Down there, life continues. The traffic is awful, stocks go on trading, and Star Trek is still showing.
grade 8 learners. Welcome to today's natural sciences lesson. My name is Patuchezo Singo, and this lesson is proudly brought to you by the Harting Department of Education. In today's lesson, we're going to be learning under the topic visible light. The subtopic, which is our main area of focus, is seeing light and refraction of light. It's part 2 because it is basically a continuation from last week's lesson. So now let's take a look at today's lesson objectives. So at the end of the lesson, you should be able to achieve these goals. Let's see what these goals are. The first objective is state how light is refracted by transparent substances. Describe the action, refraction of light on a glass prism and on lenses using light ray diagrams. So we're looking at a couple of light ray diagrams. And describe how the eye receives light energy and how this is converted to an electrical pulse which travels to the brain where they are interpreted. And then discuss the applications of refraction of light in lenses. And all of this is from your CAPS document on page 51. All right, so now let's look at pre-knowledge. So this is what we've done prior to today's lesson. In the 7th grade, we did the transfer of energy. We mainly focused on solar energy. And in the 8th grade, we've done the following. We've done reflection of light. We've done refraction of light, that's last week. And we've also done absorption of light. So that is the week before the last one. So now let's move on to our baseline activity. So I'm going to read out the questions, then give you time to answer them. So to send in your responses, please send them to 07957829908. You see the WhatsApp number is at the bottom of your screen. And when you do send in your responses, don't forget to type the name of your school so that we can give you recognition. So here's the first question. The first question is, what is meant by reflection of light? The second question is, define refraction. The third question is, outline the law of reflection. And the fourth question is, describe how the angle of incidence and the angle of reflection are measured. I'm going to give you 5 minutes to answer these questions. Then after 5 minutes, we will do the solutions together. Okay, welcome back. Now let's do the solutions together. Don't forget to send in your responses to the WhatsApp number that is at the bottom of the screen. So let's answer the questions together. The first question read, what is meant by reflection of light? What is meant by reflection of light? So when we talk about reflection of light, so this is when a light ray approaches a smooth, polished surface and the light ray bounces back, and this is known as the reflection of light. And then define refraction. How do we define refraction? The refraction is the change in direction of a wave passing from one medium to another caused by its change in speed. And the third question is outline the law of refraction. Do you remember it from last week? The law of reflection states that for reflection to occur, the angle of incident ray should be equal to the angle reflected. So the incident ray and the reflected ray, both of their angles should be equal. And then the fourth question is describe how the angle of incidence and the angle of reflection are measured. How do we measure those two angles? So the angle of incidence, this is the angle that is measured from the normal to the incident ray, and the angle of reflection is the angle that is measured from the normal to the reflected ray. So that's how we measure those two angles. Okay, so I'm going to give you a minute to copy down the corrections. All right, so now let's move on to terminology. So these are the terms that you're going to come across during the lesson. Let's see which terms we have today. We've got incident ray. So this is the light ray that strikes the surface of an object. Remember, we called it the incoming ray in the previous lesson. And then perpendicular, this is at a right angle relative to another line or a surface. Remember, we said the normal is always perpendicular to the surface of an object. And then normal, this is a line drawn at right angles to the surface of an object. So that is the normal. Let's look at the second batch of terminology. Okay, so refraction. What is refraction? This is the ability of a wave to change direction or bend when it passes from one medium, for example, it could be air, to another, such as glass. Remember when we're learning about how light is split, and how the colors of the white light are split. Remember when it's moving in air and then it passes through a glass prism, then they are split. So that is the medium that we're talking about. When it passes from one medium, other medium could be air, or the other medium could be glass. And then converge, to converge means to come together, and then to diverge means to go in a different direction. So those are the 6 terms that we have for today. Those are the 6 terms we have for today. So now let's talk about the interactions of light with matter. So this is a basic recall, or we're talking about how light reacts with matter. We've been learning about how light interacts with matter throughout the past 4 weeks. So there are 4 ways in which light interacts with matter. It interacts by scattering, reflecting, absorptions, and transmissions, or rather refractions. Okay, so what exactly do I mean? So when light strikes a smooth surface, what happens? It is reflected. So the first interaction is reflection. And then when light passes through a transparent object or a transparent substance, what happens? It is able to pass. We call that transmission. And then when when all the colors of the rainbow, all the 7 colors of the rainbow are absorbed by a surface, we call it absorption. And what does your eye record? Your eye records the color black. So when you see the color black, it means the light all the 7 colors would have been absorbed by that surface. And then scattering, remember when we learned about scattering, we learned that when light strikes a rough surface, it scatters. When it strikes a rough surface, it scatters. So these are the 4 interactions that light has with matter, and we have learned them over the past weeks. So now let's have a brief recap of the refraction of light. This is very, very important as it is related to today's lesson. So when light travels from one transparent material to another, it refracts. What does it mean? It's going to bend. Remember, we learned that light travels in straight lines from our first lesson when we're learning about visible light. So when that light is moving in that straight line, and then it travels through a transparent material, and then it travels from one to another transparent material, it's going to bend, or it's going to refract. So different wavelengths of light refract by different amounts, meaning they bend by different amounts. So this explains why the glass prism disperses white light into the 7 colors of the rainbow. Okay, so the different colors of light will refract at different angles. So when we're measuring those angles are going to be quite different. I'm just going to pull up a picture there just to show you how the different lights bend, how differently they bend. So we have white light coming in, it's our incoming ray, and then it's moving in air. And then now it reaches this material, this glass prism. It's going to bend, and as it exits the glass prism to go into the air once again, it bends again. So we are able to see the different colors here because they have different wavelengths. And because of those different wavelengths, that's why they bend, or that's why they refract by different amounts. That's why you're going to see red there at the top, orange, yellow, green, blue, indigo, and violet. Because of their different wavelengths, they're going to refract in different ways. So now let's talk about refraction of light through a triangular prism. So light enters the glass at an angle to the normal and refracted towards the normal. So on the second surface of the glass, the light is refracted again, but the normal of the second side is not parallel to the normal of the first surface. What do I mean? Okay, so this is why the light changes direction completely, because when it first strikes the first side or the first surface of the triangular prism, it's going to bend. That much we agree, that much we've learned. We now know that when a light is moving from one medium into another medium, it's going to bend, it's going to refract. So as it hits the second surface of the prism, on its way out, it's going to bend again. So that's the reason behind the changing of direction of the light. So light would have traveled from glass to air and is therefore refracted away from the normal. So let's look at this picture. So the first time it hits the first side, so there's side number 1 and there's side number 2. Okay, so light is moving in air and then it enters the glass at an angle. Now, it's at an angle to the normal. Remember, the normal is always at right angles to the surface. And remember, the triangular prism is slanted, so our right angle is not going to be a straight line like this one here, because the triangular prism is slanted. So our right angle is going to be slanted. So it's going to be in this direction. So light enters the glass and then it is refracted. You see it has refracted the light bends. It's no longer moving in this straight direction. So when it reaches the second surface, which is the second surface? This is the second surface here. This side is the second surface. So when it reaches the second surface of the glass, it is refracted again. It bends again because it's moving from another medium. It's moving from this medium glass back to air. So it moved from air to glass and it was refracted. Now it's moving from glass to air. So now that it's moving from glass to air, it's refracted again away from the normal. Away from the normal. Okay, so now I hope you understand. So now let's move on to our first activity. The first question is, what is the normal? The second question is, what are the incident ray and refracted ray? And the third question is, draw a ray diagram of refraction of light showing the incident ray and the refracted ray, including the normal, through a rectangular prism. A rectangular prism. And the fourth question is, draw a ray diagram of refraction of light showing the incident ray and the refracted ray, including the normal, through a triangular prism. Through a triangular prism. I'm going to give you 5 minutes to do this activity. Don't forget to send in your solutions to 079-578-2908. See you after 5 minutes. Welcome back. Now let's do the corrections together. The first question was, what is the normal? The normal is a line drawn at right angles to the surface of an object. It's drawn at right angles to the surface of an object. And then what is the incident ray and the refracted ray? What are those? So the incident ray is the ray that strikes the surface of an object, the ray which has entered the second medium and bent either way from the normal or towards the away from the normal or towards the normal, depending on the density of the new medium in the comparison of the old one. Okay, and draw a ray diagram of refraction of light showing the incident ray and the refracted ray, including the normal, through a rectangular prism. So the keywords that you're focusing on, what kind of prism are we drawing? We're drawing a rectangular prism. What do we need to draw? We need to draw a ray diagram of refraction showing how many rays. We need to see the incident ray and the refracted ray. What other ray do we need to see? We need to see the normal. So we need to draw a rectangular prism, draw an incident ray, refracted ray, and the normal. Right, so there we go. So this is a rectangular prism. So the key word there, the trick word was rectangular prism. So here is our incident ray entering the side, one side of the prism. And then where's the normal? The normal is always at right angles to the surface of the object. The object is a rectangular prism, so there is our normal. You draw your normal in a dotted line, use a dotted line. So once it strikes the surface, the first side, side number 1, it's going to bend. And then it's going to strike side number 2, which is surface number 2, and then it's going to bend again and exit as it exits the medium. So you need to draw normal number 2. Where is normal number 2? There is normal number 2. You represent it as a dotted line. It needs to be at a right angle. Okay, so this is your incident ray and this is your emergent ray, or rather your refracted ray. So I'm going to give you 2 minutes to copy down this diagram. I'm going to give you 2 minutes to copy down this diagram. All right, let's move on to question number 4. Question number 4 reads, draw a ray diagram of refraction of light showing the incident ray and the refracted ray, including the normal, through a triangular prism. So let's see what are the key points? What does this question want from us? So we need to draw a triangular prism. So that's step number one. We need to draw a triangular prism. And then which rays are we supposed to draw? We're supposed to draw an incident ray, a refract, and a reflected ray. What else are we supposed to draw? We are supposed to show the normal. So we're supposed to show incident ray, refracted ray, and the two normals, and then all of this on a triangular prism. Let's look at the diagram. So here is our refract incident ray. It's coming in, our incoming ray. Once it hits surface number one from the air, it hits surface number one of the prism, it bends, and then once it hits surface number two, it bends again. So you need to show that the ray was bending, and then make sure you label. You need to label, and then you need to show us the normal. The normal on a triangular prism is a bit tricky. It is a bit tricky. If you're not sure, just turn your book around or turn your paper around and make sure that your normal is at a right angle to the side of the prism, of the triangular prism. Make sure you can turn your book around just to make sure you draw your nice dotted line at a right angle. I know it could be a bit tricky because the sides are slanted. So you can turn your book around and draw the line. So I'm going to give you 2 minutes to carefully copy down this diagram. Welcome back. I'm sure you had quite a bit of time to copy down the diagram. Now let's move on to seeing light. We've covered refraction of light. Now let's move on to seeing light. So here we're basically learning how we see light. So light of different frequencies passes through the cornea because it is transparent. The cornea is the front part of your eye. So it enters the eye through the pupil and travels to the retina. So this is the cornea. There's cornea, it's labeled there. So this is the cornea. So light of different frequencies, remember different lights have different frequencies from the 7 colors of the rainbow. So they all enter the eye through the cornea. So once they pass the cornea, they enter through the pupil. So which part is the pupil? The pupil is this gap here. That gap between inside of the iris, that is the pupil. So the light is going to pass through the cornea and then go in and pass, and we're at the pupil there. So once it passes through the pupil, it travels through to the retina. If you remember from our terminology, we said the retina is made up of light-sensitive cells, So it passes through the cornea, through the pupil, and it goes to the retina. This is the yellow surface there. That's the yellow surface. The retina is made up of light-sensitive cells. So these are called receptors. So these are specialized receptor cells in the eye's retina. So once the light hits the specialized cells of the retina, what's going to happen? Those specialized cells are going to be stimulated. They are stimulated by the specific frequencies or colors. I'm going to be using the words frequency and color interchangeably. So now remember each color, red, orange, yellow, green, blue, indigo, and violet. Each of the 7 colors has their own wavelength and their own frequency. So that's how our retina cells, those specialized receptor cells that are found in the retina, that's how they are stimulated. They are stimulated accordingly by the different frequencies. So the light energy that then forms an image that you see on the retina is converted into electrical nerve impulses. So the light has gone into the eye and then it has stimulated the light sensitive receptor cells, and then that is converted to electrical nerve impulses. Then what happens next? Now, what happens is that these electrical nerve impulses then travel through the optic nerve. Which one is the optic nerve? That's the optic nerve there. So they travel through the optic nerve to the brain, which then interprets the impulse and tells us what we are seeing. So an electrical nerve impulse is like a message. So what happens is light enters the eye through the cornea. It goes from the cornea to the pupil. It also passes the lens there, so it's moving there, and then it strikes the light sensitive receptor cells that are found on the retina. And then once it strikes those cells, it stimulates them to form an impulse, an electrical impulse, which is a message. Those impulses are then move into the optic nerve, and then the optic nerve sends them to the brain. So once they reach the brain then interprets the color that you are seeing. If you are looking at a yellow dress, the brain is going to then interpret you seeing that yellow dress. If you are seeing a red dress, the brain is then going to interpret that you're seeing a red dress. Okay, so that's how we see light. That's how our eyes function, or our eyes see light. So once again, what are the stages of a path of a light ray in the eye? So we start off at the cornea, then it moves on to the pupil, then the lens, then the retina, the optical nerve, and then lastly the brain. This happens in a fraction of a second, in a split second. You won't even feel or recognize the delay. There's no delay. It happens so quick. The electrical impulses move so quick. Remember, we said light travels at a very, very fast speed. In space, it travels from space to Earth, it travels at 300,000 kilometers per second. So can you imagine the speed of light when it enters your eye, and then to get the message all the way to the brain, it happens in a split second. You won't even notice the delay. So once again, the light travels from the cornea and then moves through the opening, the pupil. Then it passes the lens. So it moves from the cornea to the pupil. It passes the lens, then to the retina, where we've got our light sensitive receptor cells. Then from the retina, the stimulation or the stimulus is converted to an impulse. That impulse is then carried by the optic nerve, and then from the optic nerve, then it reaches the brain. Then the brain interprets what you are seeing. Then the brain interprets what you are seeing. So what we actually see is light and not objects. Okay? So now, why do objects appear to have a certain color? So now we know how the light travels from the air to the eye, to the brain, and then to our interpretation of what we are looking at. So why do they appear to be a certain color? So think about a yellow sunflower. I like the color yellow. So why do sunflowers' petals appear to be yellow? Why do you think they appear to be yellow? There's the sunflower. I just pulled up a picture of a sunflower. What are the petals? Those are the petals. Those yellow parts, that's what we call petals. So those are the petals of the sunflower. Why do you think they appear yellow when you're looking at the picture? So remember, we receive white light from the sun. So white light from the sun shines on the petals of the sunflower. So it shines on the petals of the sunflower. Once it has shined on the petals of the sunflower, the petals absorb all the colors of the spectrum except yellow. So it's going to absorb the color red, orange, green, blue, indigo, and violet. It's going to absorb all the other colors save for one color. What is that color? Yellow. So once that has happened, what happens next? So there we go. So we are looking at the sunflower. So this is the surface of the petal. This is the surface of the petal, and you are looking at it. It's going to absorb 1, 2, 3, 4, 5, 6 colors of the spectrum. But one color is going to be reflected. Remember when we were talking about the interactions of light with matter at the very beginning of today's lesson? We said one of those interactions is absorption, where we are having the 6 colors being absorbed, and the second one is reflection. So yellow, the color yellow is being reflected. So since only yellow light is being reflected to the eye and all the other colors are absorbed, only yellow light will reach the eye's retina. So the yellow light is going to go into the eye, past the cornea, the pupil, the lens, it reaches the retina. So that color yellow has reached the retina. What happens at the retina? Remember, the retina has specialized receptor cells that are able to detect a wavelength and a frequency. So all these colors have their own special, unique wavelengths and frequencies. So once that color yellow, that colored yellow ray reaches the receptors of the retina, what is it going to do? Those are going to be stimulated, and then they'll send an electrical nerve impulse. That impulse is going to be sent to the brain, and the brain will interpret that we received a certain wavelength. What color could it be? And that color is yellow. Then your brain interprets it as yellow. Then what do you see? You see the color yellow, a very bright sunflower. Okay, so this is how we see. We see colors are reflected into our eyes, light rays are reflected into our eyes, and then our eyes convert that information to a stimulus or a nerve impulse. Then the brain interprets that information. That's how we are able to see certain colors of objects. That's how we're able to see certain colors of object. So now let's talk about refraction through a lens. Refraction through a lens. So when light travels from air to glass, it reflects towards the normal. So in the case of a curved surface, the normal will be perpendicular to the tangent on the surface. The parallel light rays then enter and leave the lens. They refract to eventually focus on a specific point. So they all eventually focus on one specific point. So now this is light entering, so it's moving from air. This is to glass. This is our glass. This is our lens. So it's moving in this line. So when the light is traveling from the air to the glass, then it hits the surface of the glass. It reflects towards the normal. You see where the normal is inside of the glass. So it reflects in that direction. It bends towards the normal. It's going to bend towards the normal. Remember, the normal is perpendicular to the surface of the object. So it's going to bend towards the normal. But in the case of a curved surface, not all surfaces are flat. Not all surfaces are flat. Remember when we're learning about rough surfaces? Not all surfaces are flat. Some smooth surfaces are actually curved. So in this case, we have this curved surface here. So in the case of a surface that is curved like this one, the normal will be perpendicular to the tangent on the surface. Okay, now the parallel light rays then enter. See, now they've entered and they leave the lens. Once they leave the lens, they refract again. They'll bend again. So they bend once here, they're bending again there, and eventually focus on one point. That's what's eventually going to happen. They'll eventually focus on one point. Okay. So these rays are focused on, or we say they converge to. Remember, converge means come together. It means come together. They converge to a specific point because the lens is convex. In other words, it curves outside. So that lens that is curved is convex because it is curving on the outside, that rugby ball shape. Okay, so there is our convex lens. The light rays are coming in straight. They hit the first surface of the lens, they bend, they hit the second surface of the lens, they bend again, and then they all converge, or they all come together to this point. Okay. Now, concave lens. What is a concave lens? We've learned about a convex lens, the one that's curved on the outside. And now we're learning about the concave lens. So this is the lens, this one. This one has its surface curved inwards. It is thinner in the middle and wider at the edges. The first one was wider in the middle and thinner at the edges. So these two are opposites. So a divergent lens refracts the light entering it and bends the light rays away from each other. So the light rays can be traced back to a focal point in front of the lens. So when you look at the concave lens, the one that is curved inwards, just look at it. There's our lens there. It's curved inwards. So this is the focal point here. This is the focal point. So a diverging lens, remember we said diverge means move in different directions. So a divergent lens refracts the light entering it and bends the light rays away from each other. So if the light rays are entering from this direction, they are going to be refracted like that. They diverge. They move away from each other. They scatter. So now, how can we use this information that we have? How can we manipulate the concave lens and the convex lens? So amongst other things, lenses are used in practice to focus or to bend light. So remember, we need to use this to advantage to focus or to bend light. Remember when we're learning about the pinhole camera, how we are able to focus light. And we can also use it to enlarge images. We can use them to enlarge images, to make small images much, much bigger. And we can also use lenses to correct eyesight. We can also use them to correct eyesight. I'm sure you spotted one or two people wearing spectacles. So that's one of the uses of lenses. Okay, another use of lenses is to correct short-sightedness. What is short-sightedness? So short-sightedness is corrected using a concave lens. So this is the lens that is curved on the inside. So which is placed in front of a myopic eye. What is a myopic eye? An eye that is suffering from short-sightedness. So moving the image back to the retina and making it clear. Okay? And then long-sightedness is corrected using a convex lens, which is an outward facing lens. So I've got a picture here of how eyesight can be corrected using a lens. So we'll start off with the short-sightedness. Now, so this is someone suffering from short-sightedness. You see where the focal point is. The focal point is before the retina. So the light rays are not focusing at the retina and the image is not forming where it's supposed to form. So now with a concave lens, the light rays can then be bent in such a way that the image forms at the retina. The image forms at the retina, and then with long-sightedness, this means these people can see things that are far, but they cannot see things that are near. And then with short-sightedness, these people can see things that are near very clearly, but they cannot see things that are far clearly. So with a long-sighted person, we use a convex lens to correct this. We use a convex lens to correct that. Okay. Now, so a telescope is another example of how we can use lenses. So it is a tool that astronomers use to see objects that are far away. So most telescopes and all large telescopes, you work by using lenses to gather and focus light in the night sky. So there's a picture of a telescope. So there's a video there with the different lenses and refractive surfaces that they use for a telescope. So it is used to see things that are far, like the constellation of stars. So astronomers use telescopes to be able to see those stars very, very clearly. So now we've reached our second activity. So I need you to fill in the missing spaces. So there's number 1, we've got incident ray blank, and then the B, there's blank, and there's the light ray moving in the glass rectangle. Then we've got angle of incidence. We need to fill in this blank, and we've got a missing term, and then you need to write what the term means. So if there's a term, you need to write a description of it or the definition of that term, and if there is a description, you need to fill in the appropriate term. So you need to fill in the description for incidence ray, and then for B, you need to fill in the term, and then for C, you need to fill in the description or the definition, and then for D, you need to match or you need to fill in the term for that particular description. I'm going to give you 4 minutes to answer these questions. together. So incident ray, what is the appropriate description? So this is the light ray entering the glass from air, that is the incident ray. And then what is the term for this description? The light ray moving in the glass rectangle, that is the refracted ray, that is the refracted ray. Remember, we've got the incident ray, the refracted ray, and the reflected ray. So now how do we describe the angle of incident? What's the description for that one? It is the angle between the incident ray and the normal. So that is the description. And then what is the term that matches this description? It is the angle between the refracted ray and the normal. Where is it? We've got the angle of refraction. We've got the angle of refraction. Okay, grade 8. Now we've reached the summary. So this is where we remind each other of what we have learned today. So what have we learned today? Today we learned that in the eye, light energy is converted to electrical nerve impulses, and these impulses travel to the brain, and the brain interprets them as what we see. We also learned that light can be refracted by transparent substances. It can be refracted by transparent substances, and when light travels from air to another transparent medium, the light changes direction towards the normal in that medium. And when light leaves the transparent medium, it changes direction away from the normal. Okay. So, what else? So, a triangular prism can reflect and disperse white light into the colors we see on the rainbow. So, it can disperse them into the 7 colors we see in the rainbow. And a lens can reflect and focus light. A lens is capable of reflecting and focusing light. So, this is how a rectangular prism is able of this, it can reflect and disperse white light. Okay, what else did we learn? We learned that objects around us reflect or radiate light with different frequencies that enter the eye. So what we actually see is light and not objects. Okay, so share that with someone else who doesn't know. So specialized receptor cells in the eye's retina react to specific frequencies or colors. So those are the different frequencies that we have, with red having the longest wavelength of the 7 colors and violet having the shortest wavelength of the 7 colors. And our light sensitive, or those receptor cells that are found on the retina, are able to differentiate the different frequencies and wavelengths of different colors. That's how special our eyes are. Okay, so please do send in your WhatsApp questions to 079-578-2908. We'll be waiting to give you questions and responses as well. Right, so we've reached the homework page. I'm going to give you 2 minutes to copy down the homework questions, and then after 2 minutes, we'll wrap up our lesson. Welcome back. So when this lesson ends, don't forget to click on the complete and continue tab. And until next term, thank you so much for joining me in today's lesson. See you in term 4. Bye-bye.